So hello and welcome to Using Circos in Galaxy Australia. My name's Christina Hall and I'm the Australian Biocommons Training and Communications Manager. The Australian Biocommons is building digital capability for life science research with the goal of ensuring Australian researchers remain globally competitive. We aim to provide better access to the tools, methods and training researchers require in environmental, agricultural and biomedical sciences. We're very excited to have you join us today, and as you can see on your screens, we have venues joining from all around. You're sitting in one of 7 groups that took up the offer of training, and you're one of more than 90 individuals who have registered today. The people who have made your training at your venue today possible are the local facilitators. This group of committed volunteers has worked with us ahead of time to learn everything they need to know to assist you today. And we're going to pause here for just a minute so that the facilitators in your rooms can identify themselves. So facilitators, can you please stand up for a moment and tell everyone your name and perhaps let your room know what you're working on right now or why you're here today. Over to the facilitators. Okay, thanks for that. A couple of people who are not visible but who are totally essential are members of the Galaxy Australia team. Gareth Price and Simon Gladman are standing by to ensure that everything runs smoothly today. Now, just before we begin, a few points on how to get involved in the session. You should have all opened the schedule by now, and all the links you need for today and the indicative timings are in there. Our trainer will be delivering the content from Melbourne, and all other sites will be muted throughout the workshop to stop background noise. Your facilitators will interact with us via the chat window or unmute if there's a problem. Now, if your site is having a big problem, don't worry, your facilitator will let us know and we'll wait until we can all progress together. You're all strongly encouraged to use the shared discussion board. You can put your questions in here so that other participants, facilitators and our lead trainer can answer your questions or make comments as we go along. I'd also like to draw your attention to the link at the top of the discussion board. That's our code of conduct. In a nutshell, all participants at our events are expected to make our time together welcoming for everyone and to show respect and courtesy at all times. Finally, if you want to revisit any of today's training, the recording will be made available on the Australian Biocommons YouTube channel for your future reference, and we'll let you know by email when that's available. So now, we're thrilled to bring you today using Circos in Galaxy Australia. So our trainer today is Martin Krzywinski from Canada's Michael Smith Genome Sciences Centre at BC, Canada. Martin works in bioinformatics, data visualization, science communication, and the interface of science and art. He applies design, both data and artistic, to assist discovery, explanation, and engagement with scientific data and concepts. Martin's the creator of Circos and Hive Plots, and his information graphics have appeared in the New York Times, Wired, Scientific American, and on covers of numerous books and scientific journals such as Nature and Genome Research. He's a co-author of Nature Methods, Points of View and Points of Significance columns. We really appreciate the time Martin's offered to train us and train you in using Circos. And we're particularly pleased he's taken up the challenge to present this within the context of Galaxy Australia. So I'm going to hand over to Martin for today's session.
Hi, good afternoon, everyone. Welcome. I'm Martin, and we have 3 hours together, and I hope that during this time, which will not drag on for too long for too many of you, you will learn something about visualization, Circos, regardless of what your background level is. I'd like to thank Christina very much for organizing this, Gareth for teaching me the bits of galaxy that I did not know, which is quite a bit. Thanks for all the local facilitators. You guys have a hard job. Don't give up. Finally, thank you, Helena, from the Galaxy community for writing the Circos wrapper in Galaxy, which is what makes this session possible. So I think you should know where the whole thing started. It was a rather accidental start. One time I saw a figure like this and I thought science cannot proceed as long as we're looking at figures like this. What is this anyway? This is quite an old figure. It's from the Venter paper that published a genome sequence of human. What you're seeing is a segmental duplication within the human genome. Each of these panels corresponds to one chromosome, chromosome 1, and all the ways in which it's similar to other chromosomes. This is chromosome 2, and all the ways it's similar to other chromosomes, and this goes on forever. And by now, I'm sure you already don't understand the point of this figure. So Circos takes the approach of drawing the genome around in a circular configuration and then connecting regions that are similar or otherwise related through curves. That's essentially it, and I'm sure you probably know that by now, but it's worth saying. It's appeared in quite a lot of different places, and perhaps this is why you have an interest in it. Lots of magazines and lots of journals. It appears a lot in primary research literature when people attempt to show visual signatures of things like mutations. It appears in newspapers when people try to say science is happening and cancer science is happening. So they would draw Circos images. Here people are probably talking about what does this all mean anyway. It appears in kind of public science-related journals, again, showing something complicated to imply that there is a cancer dilemma and we need to solve it. It has appeared in artistic installations that try to teach the public about things like genomic conservation and synteny. It's appeared in pop culture. I made this figure for Wired. I never did tell them that I actually never liked the show Lost anyway, but this figure displays the relationship between all the characters in the show. As you can see, it's rather complicated, and I guess this is why the show went on for such a long time. Sometimes people use it to indicate relationships. This is urban planning somewhere in Italy. I guess things are related, and so why not show them as ribbons? People make art out of it that you can hold and touch, and perhaps the lowest form of communication, it also has appeared in advertising. So if you want to get your package from some place to some other place, be assured DHL probably connects these two cities with a line. You can look at the website, circos.ca, that gives you more information and examples of how it's used, and it includes all the tutorials and all the details about running it. It does not contain any training information about how to use it within Galaxy yet, but I hope to add it. Now, the reason why Circos is still around, I published quite a while ago, is because it's quite flexible in the sense that it doesn't perform any analysis. All it does is it draws data. You have to generate the analysis. You have to prepare your data yourself, meaning you are free to use any tool you like. And all it does is draw it. And because drawing data is something that doesn't really need to change that often, but all the analysis packages change quite quickly and quite often, Circos is hung around. On the website, you can see a variety of examples of how it's been used in the primary literature. So if you are wanting some inspiration about how to draw your data, you might find an example that's close to yours in hundreds of examples that are online. For example, you can use it to draw a human genome, connect regions that are somehow related, and superimpose other tracks like histograms and so on. The babies are not part of Circos features. It does not draw babies, just in case you're thinking, wow, that's amazing. Often what it's used for is comparing two genomes. For example, on the bottom, you see certain dog chromosomes. At the top, you see human chromosomes. And here is a synteny map between the dog genome and the human genome, because dog is a man's best friend, quote unquote. We, of course, have to share genome structures with it. You can superimpose all sorts of other tracks on top of your image, move data around to get quite a detailed view of what you're trying to show. Now, I have to, of course, let you know that there's a limit to how much you want to put into your figure, because when it's something that's very small on the page, people obviously won't be able to see it. But also this kind of information doesn't have a very good overview characteristic, in a sense of it's really hard to know what exactly is going on. And then if I need to look more closely, I will. So just showing you that you can have a detailed view and you can have overviews within Circos. For example, for each dog chromosome, CF1, CF2, canis familiaris 1, 2, 3, and so on, you can draw the alignments to the human genome to show how the synteny blocks on each chromosome appear. You can also have figures, Circos figures, without any links, any connections between genomes. Here's one from the New York Times that shows methylation levels of different tissues. And you can see that there's quite a lot of detail here. There is locations of genes, and then there's methylation within these gene locations. And they're highlighted based on a variety of conditions. So just because it doesn't have links does not mean that you cannot use Circos. That being said, I must say this, and if I did not say this, I would be irresponsible. Most of the time, you do not need a Circos plot. Now, I know you're going to want to rush out of this workshop and perhaps either get a beer or draw your first Circos figure, and one of those is fine. The other, you may not need it. Now, once in a while, it's actually a good answer, and it's actually the appropriate tool to use. And so what I want you to think about during the workshop is that you're learning how to use a tool out of many tools that are out there. And sometimes it is a good tool. It will teach you how to maybe interpret Circos figures when you come across them, spot those that should have never been created, and perhaps find reasons why you should create yours. So I leave that point there. So what are we going to do today using a Galaxy Australia? Here's a sneak peek. We have two sets of sessions that will be broken up by a short break. In the beginning of the session, we will draw a very simple image and then add some tracks to build it up to a relatively simple image still, but one that contains some data. And no later than 3:20, we'll spend 10 to 15 minutes taking your questions based on the first session. So first, what we'll do is we will just draw the human chromosomes. Here they are. They're going to have some labels. That'll be the very first image. These are your axes for your data. They can be anything in a Circos figure. They could be any sets of intervals. They don't have to be chromosomes. They could be chunks of chromosomes. They don't have to be chromosomes from the same genome. But for the purpose of this tutorial, we'll just use the human genome because it seems like quite anthropomorphic, right? We'll add some scale ticks so that you can orient yourself. I should point out that you don't always need these ticks, and a lot of figures have a lot of ticks that are really not that necessary because, you know, megabase precision is not important. So keep in mind not to make your ticks too dense. We'll kind of add the reason for Circos' existence in first, which are the links. These are segmental duplications. These are regions in the human genome that are similar to one another. They have at least 90% sequence similarity, and I think by definition, they have to be bigger than a KB. We'll then add histogram of the count of the segmented duplications in 5 meg windows. And then we'll move things around so that we have a little bit more room to interpret the histogram and see the links. Finally, we'll add in a scatter track of some copy number variation averaged over windows of 1 meg. Always keep in mind that this human genome, this axis, this haploid genome is 3 billion bases. There are 3 billion positions at which a data may appear. And you do not have that many pixels on your screen. The circumference of this circle, I'm going to say, is around 3,000 pixels on your screen, give or take. And so a certain amount of downsampling is necessary. The copy numbers here downsampled into 1 megs and the histogram into 5. Always be thinking about the fact that you will need to downsample your data for it to be visible and meaningfully interpreted. Then we'll have a break, because that's a good place to break. And then after the break, we'll have a second session. And in the second session, we will take the image from the first session, and we will make it a little bit more productive and interesting by adjusting how the data are displayed using Circos rules, which changes the format of the data based on things like position or value. So the first thing that we'll do is we'll take that copy number scatter plot, and we will change the negative values red and the positive value blue. This highlights areas faster than looking at their positions of the plots. We'll then add another scatter track with square glyphs to indicate regions where copy number values are low or high. And we'll also highlight all the links from chromosome 7 and fade away all the other ones. This is an important part of Circos, this idea that once you've drawn your data, you then use these rules to change how data are shown to focus on the patterns that are meaningful to you and for you to communicate. We'll then superimpose a histogram track on top of the copy number values, showing you the min and max values. So we'll have this track that actually is quite complicated. It shows both the min and max values in 1 meg. It shows the average value. And then we'll have these areas of positive and negative copy numbers. So it'll be quite informative because, of course, if you average things out over 5 megs, you're going to lose a lot of the details and the variability within those windows. Here's a close-up of what that looks like. We'll then add cytogenetic bands. As you know, the chromatin packing in the chromosomes makes the chromosomes respond differently to stains, and some parts can be darker and lighter, and they've been used as positional markers in cytogenetics for a long time, and sometimes people like to draw these bands to help them orient themselves on the chromosome. My view of it is, unless you know what the pattern is, forget about it. You know, I could have rearranged these randomly and you wouldn't know. In fact, you don't know if this is the right band pattern, right? So there's limited value in that. However, the functionality is there, and I'll show you how to use it. We'll then filter the chromosomes and only show 8, so that, you know, a lot of times certain chromosomes don't have as much interesting data as others, and showing them just uses real estate. We'll then apply a few more rules if we get this far to remove the in-track chromosomal links. So any segmental duplications whose ends are on the same chromosome, I've decided to remove from the figure and make all the other links gray. And so that will be kind of the final image that we will be working towards. There is a document with your questions where you can post your questions. I will try to address vital questions as they come up. I have Christina here who will point them out to me. I'll address other questions during the breaks, and at the end of the tutorial, all of them will be answered in that document after a day or so. So if you have any concerns, you have any questions, please jot them down. So your data files for today, what you need some data to draw. What are they? Well, I want to show you what the data file format looks like. One, because it's very, very simple and easy to understand. And two, just because you are using a wrapper to drive Circos, there may be a day when you want to drive it yourself. And also understanding the underlying data set is really important to, in all cases, to try to help you filter and select and combine data sets together. So the first data set, the first data file, is the definition of the chromosomes. So their names minimally, so that you can refer to them in other data files, and their sizes, and for the purpose of formatting their color. What you will see here is chromosomes whose names are HS1, HS2, HS3, and so on. Circos names chromosomes. Well, I guess when I say Circos names them, I mean I name them because I wrote Circos, but that is another level. they're named after the genus and species of the corresponding genome. And the reason for that is if you want to have chromosomes from different genomes, they can't all be named CHR1. And because every chromosome has to have a different name. So for human, it's HS1, Homo sapiens. For mouse, traditionally, they're MM, mus musculus 1, 2, and 3, and so on. So here's the karyotype file. Here's the name of the chromosome as is referred to in the data file. Here's the label. Here's the start and the end. This is the size. And then the last column is just the color that it is shown up in by default. So every chromosome has its color. For the 2D data tracks like lines, scatter, or bar charts that we'll draw, the data file is very, very simple. It's like a bed format, basically the chromosome, the start and the end of the bin, and then the value. So this is a histogram. This is the copy number, average copy number in 1 meg windows. So here's a 1 meg window, and here's the average copy number. Very, very straightforward. Links, so those ribbons, those connections between two genomes, the format of this is as simple as it can be, which on every line is essentially a pair of genomic coordinates from here to there. That's it. There are other things that can be added to these data files, but we don't need to cover them right now. Okay, so between those two formats, those are really the only two format data files that Circos uses: single coordinates with a value, or pairs. What we'll also do is for the second part of today, we will have data files that have the minimum and maximum copy number values within 1 meg. So again, they will look just like the ones that are average. They will look like this, and we will use them to show the extent to which the data varies over 1 meg windows. These data files have been pre-computed and they're already available to you. Finally, the cytogenetic banding pattern is shown, and this is entirely optional, is shown in a file like this, which is very similar to the karyotype definition. Essentially, it's a band on this chromosome. The band has a name. The band starts here, it ends there, and it has a certain color, and these are the colors that are conventionally defined in genome browsers. So a certain type of gray and a certain type of light gray and red. Typically, the centromeres are red, and there's a specific red color that UCSC genome browser uses, and these are the colors that I use. So we're going to use Galaxy Australia for working through all of these images. And for the purpose of the tutorial, so that it goes as smoothly as possible, and yet it gives everyone an opportunity to practice and experiment and make, change things without affecting the rest of their tutorial experience. I've made a Galaxy history available where all the images have been pre-generated and all the configurations for each image is available to you. So what I would like you to do now is import that history into your workspace, and you can find that history by going to the Shared Data tab and Histories in Galaxy Australia. And this will bring up a search box where you can look through all of the histories that have been published by other people. And if you type in Circos, you will see, I don't know, at this point, at least 2 histories. The one called Circos Workshop version 2 Australia Biocommons is the one that we're going to be using. There may be others. And if you click on that Circos Workshop version 2 history, what you'll see is that you're going to be brought into a view of the kinds of items that are in that history. And you'll want to import that history into your space so that you can start working on it, because right now it's in my account. And you can do that by clicking on the plus button in the top right of the screen, right next to About This History. So once you've imported that history, that's now in your space, and you can do with it as you like. What you'll see when you import that history is that there's a bunch of things that have already been made. And I've made these so that the tutorial runs reasonably smoothly. There's going to be a bunch of images that have been prepared. All of these images have names that try to suggest what is shown on the image. For example, the first one you saw in the brief intro is the karyotype only image, working all the way up to the zoom 2 image where we've zoomed in on 8 chromosomes and so on. And these numbers don't worry about what the numbers mean. That's just the order in which I made the images. And then at the bottom of the history are the data files that we'll be using. The karyotype file, the definition of the chromosomes, the bands, the copy number, average, min, and max in 1 meg windows, the segmental duplication links, and then their counts. These names, I've just given them arbitrarily like this. Of course, the files can be named whatever you like. So if you scroll down in the Galaxy page, once your history has been imported, what you'll be able to see is click on the eyeball. Sorry, click on the eyeball icon, for example, next to a data file, and what that will show you is that will show you that data file that is there. Don't worry about the fact that the columns have not been assigned correctly by Galaxy. That's just a formatting issue in the wrapper. That's not a big deal. But essentially, you see the label of the chromosome and the start and the end and the color. So we'll take our first step. We'll draw the chromosomes. Okay, excellent. Now, there's a couple of ways in which we could do this. And what I'm going to be showing you is the setup for that image, which has already been created. So if you, for example, search for Circos in the tools panel on the left in Galaxy, you'll be taken to a variety of Circos related tools that you can use. And there's one called Visualizes Data in a Circular Layout, Circos, and that is the wrapper that we'll be using today. That's the wrapper that Helena wrote. Okay, so when you click on that, you'll be taken to this screen. And essentially what the wrapper does, it's a very, very large web form. And this web form has certain collapsed elements like ideogram, ticks, and highlights and outputs. And all of these things, when you open them up, they contain more fields and so on. And all of them go to define how to create an image by specifying things like data, the position of the tracks, and so on. And so we'll start at the beginning and we'll build one up. For example, if you go to the karyotype section, which is the first panel, you can select reference genome source as the karyotype, and then in the karyotype configuration, you would choose the karyotype human AG18 file that is already part of your history using the drop-down tool, or possibly the little folder tool. So that selects the file. Obviously, that file has to be correctly formatted, and then you'd be ready to go. Now, because all the images have been pre-generated, you may choose to execute this panel to then submit a job to Galaxy to make your image. Or you can just look at the first image, which is karyotype only image in your history. That is essentially the result of submitting that job to Galaxy. And I've done that to try to minimize lag and waiting for people to have their images processed. So if you click on the little eyeball beside the karyotype only object, in the main view, you'll see a little bit of the image, which you can scroll around in. What you can also do is you can click on the little floppy. I love the concept of the floppy because 3.5-inch floppies haven't been around, but nevertheless, actually this image may not even fit on a floppy. All right, point taken. You'll be able to download that image to your local drive and do with it as you please. By default, I believe the dimensions of this image are 3,000 by 3,000 pixels. So here's that image. If you download it and if you zoom in, as you'll see, yep, that's just the chromosomes and the labels for those chromosomes. And these are the very labels that appeared in the karyotype file right next to the chromosome name. If you're wondering where these colors came from, well, I thought, well, what colors should I pick for chromosomes? Let's go to authoritative reference. The UCSC Genome Browser does have a chromosome color key that they've been using forever. Is this a great key? I don't want to answer that question, but it is one. And so Circos has colors defined or one set of colors defined like this to color your chromosomes. There are other settings, but let's not worry about them. Here's the motivation of where those colors came from. So what you can do if you like is if you click on the redo job icon under karyotype only, which is that circular two arrows rotating into one another. What this will do is this will bring you into the galaxy form that was used to generate this image, and you'll have an opportunity to change values and run that job again. So for example, if you click on that, and then if you click on execute, then you can start that job. And what will happen is that Galaxy, you'll submit the job to Galaxy, that form will be processed, it'll launch an instance of Circos, and then eventually after 20 or 30 seconds, it'll tell you that there's a job that's being processed in the queue, and then a job will appear in your history called something like 46 Circos plot, and then eventually it'll go yellow, and then it'll go green, meaning that it's done, and you can look at it, and then you can delete it from your history if you like using the X. And essentially that Circos plot will just be a copy of the karyotype plot because you've just did it with the same settings, okay? So if you want to make some changes to the settings for the images that I'll be talking about, this is what you would do, is you would make the changes, execute, look for a new item in your history, look at it, is it good, is it bad? You could keep it or you could delete it, or you can even rename it with the pencil tool. So what we're going to do is we're going to bring up the image settings for the next image to add ticks, and then we'll progress through all of the images like this. So as I said, all the images are ready and all of the settings have been created for you so that you can look at them and edit them if you like. So go to the item 13, karyotype ticks item in your history, and that is the image where there's the karyotype and the ticks. And then if you click on the redo job icon, you'll be taken to the form that shows you all the settings, okay? So you're presented with the wrapper front page. It's already filled in the karyotype information, right? Because I've already done that. And now we're going to explore the ticks section, which is in the ticks menu group. If you click on that, you open that up, and you'll see an option, and it says to show ticks. Yes, we want to show some ticks. And the way that the ticks work is that you create groups of ticks, and each group has ticks spaced at a uniform spacing. And then by layering these groups of ticks, you can have some ticks that are more dense than others. So what you do is you would click on the insert tick group, and that will open up a menu where you can enter the tick spacing and so on. So for example, I've created a group for ticks every 20 U. Now, what is this U? That is a unit that's been previously defined in another menu item. It just stands for a megabase. So instead of typing 20 million, it's a unit, it's just some unit, and I've defined it as a meg, as a million bases, because it's a convenient unit for this size genome. So every 20 megs, I get a tick. It's going to be black, and yes, I do want a label, thank you. I want a label of size 20 pixels, and I want it as an integer, and I don't want to have a unit at the end of that label. A unit would be something like megabases, okay? No units. I will then create another tick group, and in the second tick group, I want them to be every 10 megs, and I don't want labels. So basically what I'll get is I'll get ticks every 20 megs with a label, and ticks every 10 megs, so in between those ticks without a label. And if I execute that, I'll get an image like this. And so now what you see is you see ticks every 20 megs with a label, ticks every, alternating ticks every 10 megs without a label, okay? So this is a helpful way to navigate, to add a navigation element to the image. What we'll do next is we will add on to this image the links. The segmental duplications, finally, we'll get to draw some data on top. So if you go to the next item in the history, which is 14, segdup, this is the form that creates that image. And again, you click on this rotating arrow icon to redo this job, to look at the form for that image. I won't mention this part again because we'll be doing the same thing for every image. So from the front menu of the web form, what we're going to be now doing is working with the link tracks group. This is the actual data tracks where we can drop in links that connect regions of the genome. When you click on that, you get a bunch of different values, and all of these values correspond to some aspect of that track. The first things is the inside radius, so where should the links end relative to the radius of the circle. I've put 0.9, which means that the links will end 90% out towards the edge of the circle. Using the SegDup index top 100 as a data set. That's the link data set that I showed you before. I'm going to have a basic link type. There's also a link type that draws the links as ribbons, which have a variable end thickness, but for our scale, because the genome is so large and these seg duplications are so small, if we were to draw the ends to scale, it wouldn't look any different than if we just drew them as a single line, essentially, because they're so tiny. I will make them black. I will give them a thickness of 4 pixels, and the Bezier radius is 0. This corresponds to the geometry of how the links are drawn, and I won't focus too much on it other than to say 0 is a good value to start, and you can read more about it on the Circos webpage of how these geometries are created. And that's it. That's all you need to define a link track. You see these Bezier curves, these smooth curves that connect points that are segmental duplications. The ends of these links are 90% of the way from the center of the circle to the position of the ideogram. They're black and they overlap, and there's areas that are very, very dense and hard to see, and that's fine. You can mitigate that by adding transparency and so on. Okay, I've been told to slow down. I am slowing down. So what are we going to do next is, because an image with just links is not very exciting, unless the links are extremely exciting. We'll add a histogram that shows how many segmental duplications there are. And this is item 15 in the history, in your history segdup, counts. So for this, what we'll be doing is we'll be using the 2D data tracks menu item. Now, for legacy reasons, depending on how Circos was written, a long time ago, I decided that the link tracks should be somehow quite different in organization and definition than the 2-dimensional data tracks like the scatter plot and the line plot and so on. In hindsight, that probably wasn't the best idea. They're all data tracks, and some of them can be links and some of them can be histograms. But this dichotomy remains, and so this is why in the wrapper respects that legacy decision I made, and that's why these 2D data tracks shows up as a separate item. It doesn't just say data tracks. So if you click on the 2D data tracks, here there's a lot more options than in the link track. Because you can create a variety of data tracks. So the data track is a ring, and it has a certain beginning, a position, and an end position. So we're going to have the ring begin at 90% of the radius of the circle and go all the way up to 98% of the radius of the circle. It's going to be a histogram, and it's going to use the track count segdup 5 megs as the data file. So the pre-made counts of segmental duplications. That's essentially all you need to define a data track. And there are some plot format specific options. Depending on what plot type you've selected, the wrapper will allow you to make a couple of other changes to the track, which are worth doing. So what we'll do in that section is we'll select a color, and that'll just be black. We want to fill underneath the histogram so that it's not just an outline, but there's a fill. We do not want to join non-abutting bins. For some reasons, there's an option in some cases, you may want to join areas where no data is defined, but in this case, we don't. And we do not want to orient the histogram inwards. We want the y-axis to point outwards, right, towards the edge of the circle. So those are the options for the histogram. And once we draw it, well, now you see the histogram. It's a little bit uncomfortably close to the links, right? Because we've made the links end at 90% of the radius of the circle, and we made the histogram begin exactly at 90% of the circle. So we probably want to rearrange that. And this is common. You'll draw some data tracks and you look at the image and it won't be nicely spaced out. So you can go back and refine those radial positions for each of the links to suit you. So in the next image, what I'll do is I will just adjust the track position slightly to make more room for this histogram. So what I'm going to do is I'm going to go back, and for the data tracks, the histogram inside radius, I'm going to change from 0.9 to 0.82. And for the link tracks, I'm going to change from 0.9 to 0.8, okay? So the links are going to use up less space, and the histogram is going to get a little bit more space. And the way that that will look if you execute that is like this. So that's reasonable. You can now see the bins more clearly, and that separation between the links and the bins is a really good visual boundary between those two tracks. So again, these histograms simply represent the number of links that are incident on windows at that position, and those windows are 5 megs in size. Now, optionally, you can try this if you're keen, is you can create these counts using a Galaxy wrapper as opposed to assuming that somebody will provide them for you or counting the links yourself. So there are, in the tools, in the Galaxy tools, if you search for Circos, as I showed before, there's a bunch of different other Circos related things that have been implemented. And one of them is link density track, reduce links to a density plot. Essentially what this does is it calls one of the tools that comes with Circos, takes a link track, it goes through the links, it asks you, well, what bin size do you want? 5 megs, okay. Every 5 megs, I'm going to count how many links are incident on this 5 meg window, and I'm going to produce this data as a 2D data track so that you could draw it as a histogram, for example. So you would say 5 megs here, you would select the link track in the links file, and then under use number of links rather than sum of ends, you say yes. What that means is that you could count them, as we're going to do here, because we're answering yes to the question. If you don't answer yes and answer no, what it will actually add up is the length of the link. So essentially what you'd be getting is how much of the genome in 5 meg windows belongs to a segmental duplication, okay? So that is something you may want to do. In this case, I'm just counting them. And when you do that, you get a different history item, which is a data file, and it looks like this. It looks just like that 2D histogram file that we've been using for the counts, chromosomes start, end, and the count. So that's just optional. Just know that you can use Galaxy to manipulate these data files in all sorts of ways, not just from the Circos tools, but using the data munging tools that are built into Galaxy. This is a long and big topic that I won't discuss any further, but I urge you to look into it. What we're going to do now is add another track. So the idea here is to try to build up a Circos image that's quote unquote representative of variety of enough Circos images so that it gives you an idea of how to use it for your data, because of course I don't know what your data will be. So we've added a link, great, we've added a histogram, okay, and now we're going to add a scatter plot. because that's different enough from a histogram visually, but even though it uses the same kind of data format. And for this histogram, we'll use copy number variation because traditionally that is shown as a scatter plot. Not always, but it can be. So we'll go back to the 2D data plot form. And then at the bottom of the definition of that CNV, of that link account histogram, there'll be a menu item says insert 2D data plot. So we'll make another one. Great. So we click on that. We get an option for another 2D data plot. We'll put that 84 to 96% out from the center of the circle. It'll be a scatter plot, and it'll be using the copy number 1 meg average data file as input. Okay. Now, in the format specific options, these are going to be slightly different than the histogram because this is a scatter plot. So now what we'll see is we'll see that we have an option to select a different glyph or symbol. So it'll be a circle, size 12. 12 sounds fine. Of course, when you create these plots, you may not know, well, what size should I do? You could just experiment, keeping in mind that this is in pixels and the size of the final image is 3000 pixels by 3000 pixels. We'll make it black or dark gray, and then stroke thickness 0. So the symbol, the circular symbol for the copy number will not have an outline. What you'll also have as a plot specific option here is the minimum and maximum option. So if you don't define these, what will happen is Circos will figure out what the minimum and maximum value are for a data track and use those as the bounds for the plot. What I want to do is slightly different. I want to impose a minimum and maximum value, so crop the plot to these values. And any data that falls outside that plot will be drawn at the minimum and maximum value of the plot. There's an option to hide the data, but let's just put it at the edges, okay? So we know what has been pushed out of the plot. Finally, what we'll do is we'll insert a background behind the plot. So one of the options in the menus in the form for a 2D data plot is insert a background. So here we have a background. It will start from 0 to 1. This is relative to the plot size. So from the beginning of the plot to the end of the plot, we'll get a solid ring of light gray color. This is light gray. And there is our plot. As you can see, if you look up close, it overlaps with the histogram. And I did that purposefully. And that is to show you that tracks can overlap. And if you do not select your radial positions for the beginning and end of the track, they will. And that's often not what you want. So remember, what we've done is we've drawn links which end at 80% of the radius of the circle. We had that histogram of counts, which was 82 to 98%. And then we put this scatter plot just now from 84 to 96%, and it's sitting on top of the histogram. No good. So as I've done before, we're just going to change these values around to give the tracks a little bit more breathing space. And so in the next image, what I'm going to go through is just changing those radial values to move the links a little bit closer to the center, move the histogram a little bit closer to the center so that copy number variation scatter track has some room to be shown without overlapping with the histogram. So that is in the form. Yeah, I'm not gonna show you exactly where that is because we've just been there. They're just those values. And now if you zoom in on the image, you see that there's plenty of room. The links end at 70%. Then there's a 2% gap. The histogram is 72 to 80%. And then the scatter track is 84 to 96. Okay. And you may want to, depending on how big your figure is and how much variation there is in your data, you may want to give more space for the scatter plot. You would then change these values further and, for example, make the links go to say at 50%, and then maybe dedicate 25% of the image to the scatter plot, and maybe 25% or 20% of the image to the histograms. It's up to you. Just keep in mind that if you stretch the track to be very, very thick, the data points may look like they're losing coherence and they're just scattered all over the image, and it's very difficult to track them. So whatever it looks visually appealing and whatever makes trends look more obvious, keep that in mind and use that as guidance for selecting those radial positions. So why did I pick a histogram for the counts? Why did I pick a scatter plot for the copy number variation? Those are conventional choices for things like counts or copy number variation. But keep in mind that there's no right encoding for a data set. They're just, some encodings are more conventional than others. That's all. And so be aware of the fact that sometimes if you stick with convention, people are less likely to be confused in the very instance that they see the image. And that's good. However, sometimes your data might suggest that a different encoding is better because its structure, the trends of its structure are more visible in a different encoding. And so if you use a different encoding that's not conventional, in the very instance that the person sees the plot, they might be slightly confused, but very quickly get over that confusion and then be able to get more out of the plot because you've picked a more productive encoding. So keep in mind that that initial confusion isn't always something you want to avoid, it's natural. Now, also recognize that we've used exactly the same kind of data file format for the histogram and the scatter plot. So what that means is you can go back to your image settings and change that histogram option to just plot type heat map. And you don't need to change anything else about that track because a heat map and a histogram uses exactly the same data format: chromosome, start, and color. And so you can easily change how the data are drawn just by a single setting without having to change anything. Now, there's probably a couple of plot-specific options that you'll need to change because a heat map doesn't have glyphs and a histogram doesn't have a color scale specifically. But for the most part, they're entirely interchangeable. And heat maps often require less space because you can make them really, really narrow because what's encoding the value is a color, whereas the histogram needs some vertical radial space because what's encoding the value is the size of the bin. This is a very important point in general when drawing anything on the genome, is managing scale. The genome is large, let's say the human genome, okay, it's large. And most features on it are really small. So if the genome is, haplogenome is 3 gigs and you know, your image circumference is 3,000 pixels or so on, or even 10,000 pixels, that still means that thousands of bases correspond to a single pixel. So you don't want to start doing things like drawing SNPs exactly at their position of width 1 base and hope that they will appear because they will be rendered as something that's much smaller than a pixel. So keep that in mind. If you have lots of observations like methylation values, where you may have hundreds of thousands of observations, if you draw them all on a track, you will get lots of data occlusion. You'll get lots of points that are sitting on other points. And in order for you to see that point, it'll be so big that it'll span the width of, you know, hundreds of other point positions. So the way to deal with that is there are options to add transparency to data points, to build up ink in those dense regions. And that works up to a point, so to speak, but it can fail rather quickly. One of the other options, which we're already doing in the copy number track, is to create an aggregate statistic. So for example, a median or an average, and some kind of a variation maybe, depending on whether you want a precision in the median or average. You might draw a first and fourth quartile, you might draw standard deviation, you might just want minimum maximum. across a certain number of bases. And as a rule of thumb, I suggest that given your image, don't divide it up into more than 1,000 bins, because the visual acuity being what it is, we just can't make out more detail than that without getting very, very close to the image. So if your image is in print or on a monitor, 1,000 bins generally corresponds to maybe 2 pixels, which is comfortable. Or in print, it essentially corresponds to slightly something wider than a hair, a human hair. And what you could also do is remove, to manage scale, is filter out chromosomes that don't have data or don't have interesting patterns to show. It's okay to focus on areas that are interesting at first, and then unpack the others later in your explanations. Always keep that in mind, that the first thing that you want to do is express the trends that are relevant, and then later show the context and background noise and all of these other things that in a way are subordinate to your main explanation, but do support it and do not invalidate. Finally, the last, I don't know, 10%, let's say, of most images for publication, the work required is not going to be in Circos or Galaxy. It's going to be in post-processing in something like Illustrator or Affinity Designer or whatever. So typically what you would do is you would take a Circos image, you would generate an SVG instead of a bitmap. You would import it into Illustrator or some other software, and then you can begin to adjust the stroke weight and transparency as was suitable for your exact output. And that's a lot easier to do quickly and experiment than with Circos. You can certainly do it in Circos, but you have to have those numbers available to you. Whereas with Illustrator, you can visually experiment. And then you can finally add and tweak labels to add paragraphs of explanation, if it's, let's say, a larger image for a poster, a figure, tracks for labels for tracks, and so on. So keep in mind that just because you get an image out of Circos doesn't mean that it is ready to go. It generally needs to be tweaked slightly because, well, yeah, there's a limit to how much coding I myself could do in that regard. So we're going to focus on take some questions right now from you for the first part about anything that you've seen or anything that you maybe want me to revisit.
We've got one question about can we draw differential gene expression data from sheep in Circos Galaxy? If yes, please. Where do we start?
From what?
Draw differential gene expression data from sheep.
Okay, so somebody's asking whether you can draw differential gene expression data from, presumably as output from some analysis program called sheep. So, okay, let's look at this question. I don't know what sheep is. There's some software out there that does some analysis, whatever it is. It calls variants. It gives you some gene expression values, fusions, whatever, right? And then it produces some information that's somehow formatted. And the question is, can you draw the data? The answer invariable is, of course you can. You could draw the data. How do you draw the data? And what kind of patterns are you looking to see? What is the spatial distribution of the data? How densely populated is the data? Is it expression for every gene? So there is, 20, 15,000 data points here. Is it expression for a subset of genes? There may be 1,000 data points in there. What is the extent of the differences in the expression? Are you interested in things that have very low expression and nothing else? Are you interested in things that have very high expression? What is of interest? So for example, if the latter, sure, you could look at the data set that's exported by your sheep and then extract the chromosome start and end for that gene. And then the value for the expression. This could be a log value, this could be a linearly transformed value, whatever. And you might make a scatter plot and look at it and say, you know what, all these data overlap on top of each other. I can't see what's going on. So I have to think of a different way of formatting it. If the data are very dense, you could try to show the minimum and the maximum. So you would compute the minimum and maximum and the average value. And you could show within that bin what the ranges are. You might at this point think, I wonder if Circos is the right answer for this, right? Because if I just have a genome on which I have some values, such as expression, maybe a straight line is better. Maybe I don't really care about position that much. Maybe what I care about is a list of genes, and the ones that have the biggest difference from some reference would percolate to the top of the list, regardless of where they are. So these are all considerations to think about when you have a question like, can I draw some data set? Is that the work is still left for you to do to communicate what trends you want to see and what is the spatial distribution for the data set. So invariably, if you're just looking to poke around the data set, you just want to draw it quickly, take a look at it and figure out what's going on, then Circos is probably not the place to start. You would just draw a scatter plot, let's say in R. And it'll be busy, it'll be messy, but that's where you would start, and you would learn about the extent of, you know, the variation in your data set and so on, and then start to see exactly whether what is in your data set fits with the Circos paradigm. Okay. Can you add a legend, especially for heat maps? You have, you can generate the legend if you run Circos locally, and then you would need to create the legend by hand. That's currently not implemented. Can you put an arrow at the end of the ribbon to show directionality? Yes, you can. There's a tutorial on how to do that online. If you want to work with the genome of a new species, like recently sequenced genome of Nicotiana bentamina, which I'm going to guess is some kind of a tobacco? Yeah. Okay. So what happens if you're working with a genome that has never been sequenced before, and oh my God, nobody knows anything about it, and you're the first one to characterize it? Well, first of all, congratulations. You have your own genome. And second is all right, well, you just need some axes to draw the data on. And what will those axes be? They may be chromosomes if you're that far. They may be scaffolds. They may be physical map contigs where the units are not really even physical. They're just centimorgans or something. Nevertheless, you would create a karyotype file where here the name may no longer be the relevant name, but it's still called that. And you would just specify, you know, let's say chromosome 1, 2, 3 of the chromosomes and provide the length, and there you go. Or contig, you can call them CTG1, 2, 3, and there you go. Or linkage group 1, 2, 3, whatever you wanted. You just need to figure out what the axes are. If it's something like a bacterial genome where there's only one chromosome, well, you just have one chromosome, start and end. So it's pretty straightforward. Can you do an alignment of published data sets using Circos directly? Well, no, you can't do it Circos directly. Circos doesn't generate any analysis. You would have to create that alignment, however, and then from the output of the alignment, parse it, and then create a linked data file that would have those coordinate pairs, start and end of your two alignments. Possibly with other annotations that provided alignment quality and other scores that you could use to then change how that link is shown. How do we compare genomes of different species? So when you say compare genomes of different species, that is an extremely general statement, and you could do a variety of comparisons between genomes. You can look at synteny maps, you could look at conservation, you could look at whatever, right? So let's say what you mean by that is structure. So you have two very similar genomes and they vary in a variety of places, but most of the time they're the same. So what you could do is on one half of the circle, draw genome 1, on the other half of the circle, draw genome 2, and connect regions that are similar by sequence alignment together. These plots are kind of called Jupyter plots because if the identity between the two genomes is perfect, you basically get something that looks like the planet Jupiter because you just get, you know, ribbons across the circle. In the case where the synteny isn't perfect, you'll get links that cross the image. And there you see that this is where those genomes vary. And you could then say, well, I'm going to hide all the links that do not indicate that there is any kind of shuffling going on and only leave the ones that are there. Can we add space between tracks, ideograms, between the first and last chromosome to add text in between to label track? Absolutely. I believe the wrapper doesn't support that, but towards the end, we'll get into how to edit the configuration that the wrapper generates. Basically, there's a file that allows you to specify the spacing between the ideograms, either for all pairs or for specific pairs. And so you would say, all right, the spacing between chromosome X and chromosome 1 is whatever, much bigger than by default. So I'm going to make it 5 times bigger. That will create a wedge of space, and that will allow you to place other elements within that area. In the website section that shows published images, there's a fair number of them that do this. And so just know that what you need to do to achieve that is change the spacing between ideograms. Okay, just looking through your questions. Okay, I don't have any other questions at the moment. Let's back up a little bit so I can, so for example, for the labels, what the person was asking is, can this space between chromosome X and 1 be increased so that a wedge could be created here so that text can be inserted here? Obviously that would break up a little bit the link track, but that's okay. And so yes, you can, you could do that. For general spacing between chromosomes, the spacing here could be smaller. At some point, what can happen is that if you have any tick labels from one chromosome and another, they could start to overlap if the chromosomes are very close. There are ways in the canonical Circos installation to avoid that, but the wrapper doesn't support it. If your chromosome, you know, presumably what you could do is you could even just remove the spacing between these chromosomes altogether and make the human genome made up of these 24 chromosomes look like it's one contiguous circle. That you could absolutely do that. And out of that, you would get a little bit more of space for data that is normally used for boundaries here. That may be a good idea, but it also may confuse people, because they'll be less likely to be able to identify where the chromosome starts and ends. What kind of file format do we need? Is it text like the one we used? Yeah, it's tab delimited or space delimited text. If you may, generally, if you create bed files, it's of that kind. Bed is a very generic format. It is many bed files look completely different. The only thing they have in common is the first 3 fields, I believe, are chromosomes start and end, and then whatever you want after. Basically, that's the format. Okay, if there are, oh, there's one more question coming. Including LD, presumably you mean linkage disequilibrium in the Circos plot? I'm not sure what you mean by LD. Is it linkage disequilibrium? Probably is. Linkage, it's coming, yeah, yeah, okay. Don't worry about spelling disequilibrium. It's linkage disequilibrium. So yes, you can, and I actually think that that needs its own data track because it's kind of a two-dimensional data set, and I'm going to defer answering that to when I type up the answers because I think the way you need to show it first is not ideal in a circular format because it will distort the data a little too much. But if you had to show it, I would show you how to kind of hack it in the original, in canonical Circos, so the wrapper doesn't support it. Or I would have to, you know, get a coffee and a bucket of chicken and implement this actually, so that you could use it. If you have multiple transparent tracks overlapping, can you choose which one sits on top? Excellent question. And that is one that I was going to get to later, but you're smarter than I am and you've thought ahead about it. So the way that it works in the wrapper is that whichever track you defined first in that drop-down menu on the web form is the one that's drawn first. So the second one is drawn second and therefore on top of whatever was drawn first. So they just get drawn on top. So if any of those have any transparency, which is interpreted as a linear blend, the colors just get stacked on top. I will have a chat with Helena, who wrote the wrapper, and ask her to, as one of the few quick tweaks to the wrapper, add the little feature that Circos supports, which is to allow you to independently order the tracks regardless what order they were defined in, by essentially just assigning an index number to them. So, you know, the first track might have an index number of 10 and the second track of 0 and the third track of 5, and then they would be drawn in order of that index number. So layering data is very important because sometimes you're going to want to draw things on top of other things. In particular, and I'm going to kind of jump ahead a little bit, but in answering this question, you might even expand your question to say, can I change the order in which points are drawn in a track? Because for points like copy number variation here, all these 3,000 scatter plots, the glyphs are so large that they're going to sit on top of each other. And I'm going to draw some on top of others. And if some are more important than others, then I certainly do not want the one that's more important to be overlapped by something that's less important. So the same way that tracks can have an index number that determines the order in which they're drawn, every point can have an index number that determines the order that it's drawn. So you could say, all right, values that are bigger than whatever get drawn out last, so that I'm sure they will never be covered up by other data points. So that layering is built in. It's built into links as well, where you can insist that some links are drawn on top of other links, and so on. So there's quite a bit of functionality underneath, and the wrapper does support some of it. Good question, thank you. Okay, so it is 3:20, at least here. We're going to take a 10-minute break and resume 1/2 p.m. Thank you. I'll do a quick recap of what happened and what is still to happen. So what did we do? We took a karyotype file that defined the lengths of the human chromosomes, and we drew an image with that. The colors are UCSC conventional color scheme colors, and the chromosomes have labels. We then added ticks. We added two groups. We had ticks every 20 megs that had a label and ticks every 10 megs that didn't have a label. We then added a link track. These are segmental duplications in the human genome. Now, there's many more segmental duplications than what is shown here. This is just a subset that was kept small for the purpose of this tutorial. We then added another track, a histogram track of the counts of these segmental duplications. We decided that we need a little bit more space between those tracks, so we changed the radial position values for those tracks to make the histogram a little bit larger. We then added a scatter track of copy number variation and moved the tracks around so that they were pleasingly positioned, if you will, and that will depend on your data set, but really it's just a matter of arranging the tracks using those radial limits, the inner and the outer radius. So for this session, what we're going to do is we're going to start with the previous, the last image of the previous session, and build on it in a slightly more advanced way. Advanced in the sense that it's just more details. It's not really objectively more difficult, but there's ways in which we'll look at the image that really show you, I think, the strength of Circos and any kind of application that does not confound the data with how the data is formatted. So I can keep the data file the same, but change the formatting without changing the data file. The first thing we'll do is we will add some rules that will change the color of those scatter plots, scatter points. The scatter points will be red when they're negative value and blue when they're positive. And the histogram bins will also be differently colored. They will be black when they're large and gray when the value is small. What we'll then do is we'll add more scatter plot tracks using a square instead of a circle that in a different way show the copy number data. We'll also add some rules that highlight links from chromosome 7. We'll then overlay with some transparency a histogram on top of the scatter plot that shows the minimum and maximum values. And here that question about the order of drawing becomes important. You could see that the overlay sits on top of the scatter plot track. We'll add cytogenetic bands, optional. I'm not a big fan of them, but some may demand that they're drawn. We'll then limit the figure to only 8 chromosomes. Just randomly pick something interesting is going on here, maybe. This is some kind of a funky copy number variation pattern. Here something is going on, here nothing is going on. And then we'll use the rules again to remove in-track chromosomal links and change link color and thickness, okay? And we'll wind up with an image like this. So we're, for this session, our start is history item 21. The image is rules version 1. And if you click on the rotating spinning arrows, you'll be taken to the form. Now, as you go there, I want to talk about how rules work. Essentially, there's a loop inside of Circos. And when the data are drawn, the loop looks something like this. For each track, okay, and for every data point in this track, okay, if there's a rule, we look at every rule. For every rule, if the data point passes the rule condition, okay, then the rule can have many actions. And for every action, the action is applied to the data point. Okay. Then what happens is very important. So in this case, the data point has passed the condition. All the actions of the rule have been applied to the data point. By action, I mean something like changing color or changing the glyph or changing whether it's shown or not. We go to the next data point unless flow is continue, meaning that we no longer test this data point because it's already passed one rule. We no longer test it with additional rules. As long as it matches a rule, it's done testing. So this is critical, because sometimes what you want to do is you just want to pull out data points from your data set, and as soon as they match a rule, change the way that they're formatted, and then move on to the next data point, because this one has already changed how it's formatted. But sometimes you want to keep testing the same data point even if the rule passed. Let's look at an example. So suppose you have 3 rules. The first rule tests whether the value is less than 20. The next rule tests whether the value is bigger than 100. And then final third rule tests whether the data point is on chromosome 2. Now let's say we're looking at a data point, and it's false for rule 1. It's true for rule 2. In other words, the value is bigger than 100. And it's also true for rule 3. In other words, it is on chromosome 2. By default, what happens is when this rule chain is applied to this data point, the first rule is false, so the actions won't trigger. But the second rule is true. So the actions of rule 2, whatever they may be, will trigger. And that's it. Rule 3 will never be tested on that data point because rule 2 has been applied. If flow is continuum, meaning the decision flow gets to continue, rule 3 is also tested after rule 2 is tested. And so we get to apply rule 3 actions in addition to rule 2 actions. Okay, so this helps you change the format of how your data is displayed with a lot of customization. And you may never use this feature where you're using multiple rules because your tests might be very straightforward, but this option exists. So let's take a look at this next image, rules version 1. And what we're going to do is we're going to color the histogram bins, and any values, all the values will just be gray, but the values that are bigger than 20 will be black. So let's see how that works. So in the data tracks for this image, we're going to make the fill color under plot specific format options to be gray. That makes all the histograms gray, all the bins gray. We'll set the stroke thickness to 0 as I think we did before. And now below this, there's a rules panel. And now we're going to create a rule, okay? So we're gonna click on insert conditions to apply. So these are the conditions that are going to be used to test whether a data point satisfies this rule. And when we click on that, the condition we choose is based on point value. And then we'll say 20 for points above this value. So essentially the rule is points above value 20, that's the condition. Any points that are above 20, then the condition is considered to be true, and the actions of that rule apply. What action? Well, we get to insert actions for that rule, and the action will be change the fill color for all the points. All the points meaning all the ones that passed, and we'll make them black. And that's it. That's the rule. It's a pretty straightforward rule, right? All the bins are originally gray in the track, and any that are bigger than 20 are black, okay? So I think that here what I'm doing is I'm just zooming out and giving you the rule at a glance. You have the conditions to apply. There's one condition, is the point bigger than 20? You have the actions to apply, which is just one action, change the fill color to black. Done. There we go. So nothing is moved, nothing is hidden. The only thing that's changed is by default, the histogram is gray, and then the points that are bigger than 20 are black. Pretty straightforward. Zooming in, yep, they're black, yep, they're gray. Okay. The next image, a rules version 2, adds a rule to the copy number scatter plot. And the rule is a little bit more complicated, but it's essentially belongs to the same family. By default, the points are going to be some value, like some color, like gray, light color. And then values that are less than minus 0.15 will be red, and bigger than 0.15 will be blue. Okay, so now we have two conditions. The first condition for this rule will be apply based on point value, like before. Points below this value, minus 0.15, will have their fill color change to red. And here, minus 0.15, the reason why I selected that is I decided that I didn't want the points close to 0 to be colored. I just wanted points that were non-zero and negative to be colored. This would be some cutoff that's meaningful to you where you decided, yeah, at this point, I want the points to be colored. So that's rule 1. Then I would add another rule. And there's an add rule button. And the second rule will basically look just like the first rule, except it'll be the value inverse. Points above 0.15 will have their fill color change to blue, right? So we have 2 rules. And remember that idea of flow continue and the rules being tested. There's only one rule that's being tested per point. As soon as that rule matches, no further rules are tested. Now for these rules, there's no way that a point passes both rules because it's either less than minus 0.15 or bigger than 0.15. It can't be both. So in this case, the whole flow continue thing is irrelevant. However, keep that in mind. You could very easily get to the end of these rules and neither of the rules are triggered. That would be basically for all the values between minus 0.15 and 0.15, those that remain gray, those that are drawn by default gray and are unaffected by this rule decision chain. And here's the image. You could see what's happening is that the values close to 0 between minus 0.15 and 0.15 are gray. Then the negative ones are the ones less than minus 0.15 are red. And then above 0.15 are blue, okay? And here, if you look closely where I'm pointing, you see the blue dot just peeking behind those gray dots. And that is because that blue dot was drawn first and then some gray dots were drawn on top of it because it orders the points, it draws the points, I believe, in positional order. And so here is where that option that Circos wrapper doesn't support yet, but soon it will, would come in handy where I could say, all right, well, color it blue, but also draw it on top of the gray points to make sure that I don't hide those blue dots. Here is another place where that is also of issue, okay? So now we're going to add another track and we're going to do something that's pretty common, I guess in Circos. Well, first of all, it's possible. And in the sense that it's common, as it helps you illustrate the same data in a slightly different way. And it is up to you whether you want to redundantly encode the same information into different tracks. Sometimes that's not a good idea because it implies that there's more information, whereas in fact, you don't have more information. You're just showing the same information, but in a slightly different way. And this is the image regions version 1. So what we're going to do is we're going to create a track with an inside and outside radius, which are identical, 0.82. It's going to be a scatter plot. And it's going to be all the copy number values, the same data point, the same data file as we used for the previous scatter plot. And you're probably thinking that doesn't make a lot of sense. You're drawing the same data as a scatter plot, okay? But the inside and outside radius are the same. So that means regardless of what the Y value is for that scatter plot, the points will always be at the same radius. Exactly right. And that's what I intend. And the reason why I'm intending it this way is the following. First, we're going to make all the plots a rectangle and we're going to make their color red. So as of now, basically what we're doing is we're just drawing every point in that copy number variation data file at the same radial position in red rectangle. This is pretty useless. This basically just says there is data here. But what we're going to do is we're going to create a rule which hides certain data points. Any points with a condition of greater than minus 0.15 will have their visibility changed to no. Okay, so it might take a while for you to wrap your head around it. But basically, what this track will do is only draw points that are less than minus 0.15 because all the other ones are hidden. And so this idea of drawing only a subset of the data points It's actually a very, very useful one. And you can spread the groups of points around the plot and draw one group in one track, another group in another track, and a third group, if you like, in another track, and change the formatting of the groups. Basically, what I'm doing here is only drawing points less than 0.15 at a radial position of 82%. I'm going to do the same thing for the positive points. So at 97% of the way from the inside of the circle, it's a scatter plot. The data file is the same as the average copy number variation. It's going to be a rectangle symbol, same size, but it's going to be blue. And the rule for this will be, again, symmetrically opposite. Anything below 0.15 will be hidden. Any negative values, I don't want them drawn, will be hidden. And so the effect is as follows here. I'm going to zoom in. So you see that at 82% of the way out of the circle, I have all the points that are less than minus 0.15 drawn as red squares. Here it is. That point is basically that point. These 2 points are these 2 red squares. And all of these points are these red squares. And I'm counting here on those red squares to overlap to generate what looks like an interval. Finally, for all the positive copy number values, the interval is over here. And you can see by occlusion, there are some data points here that are occluded that don't show up. I'm now going to, I've decided that, well, I don't like the fact that these two scatter plots with the rectangle symbols are so far apart from one another, so I'm going to rearrange them and place them in a slightly different position. So the copy number scatter plot will be moved to 82 to 94% of the circle. And then the first rectangular scatter plot will be moved to 97%. That's the red one, the negative values. And then the second one, the one with positive values, will be at 98%. And it looks like that. So you see what I've done is I've moved the scatter plot down, and I've moved the scatter plot with the square glyphs up. And now, if I read the figure from the outside in, the first thing that I come across is just regions. These are regions where the copy number is positive or negative. So at a glance, I can quickly see whether something is going on. If I like to look into it, I can look at the scatter plot and say, oh, well, this is the structure of the underlying data. For example, here, there's quite a big drop in copy number variation, although it's overwhelmingly still negative everywhere, and so on, okay? Again, theoretically, this idea of drawing the same data in 2 different places may not appeal to some people because it's not a very pure way of showing information. It's redundantly encoding things. However, keep in mind that this is an option and you may want to layer that detail. So in other words, you have this overview outside and then the so-called detail on demand as you look more inside the figure. So in terms of the geometry of the tracks, this is what we've done. Links to 70% and the histogram 72 to 80%, 82 to 94% for this scatter plot with circles, and then the scatter plot with the squares had the same in radius, inner and outer radius, 97% for the reds and 98% for the blues, okay? Now let's add some rules to the links, because just like 2-dimensional tracks, histograms, scatter plots, the links can also have rules. And they're built up in the same way. Essentially, every link is tested, their conditions, their actions. So what we're going to do is all the links will be opaque gray, 20% opaque gray, and then links to and from chromosome 7. Remember, Circos names the chromosomes after genus species, so it's Homo sapiens 7HS7. We're going to make those thick black and drawn on top, importantly. So item 30, rules version 3 is the image for this example. So in the link data tracts for this image, we'll set the transparency to 0.2, and here's a handy guide. If it's 0, it's fully transparent. It's 1, it's fully opaque. So this is essentially 20% opacity or 80% transparency, however you wish to think about it. And now the rule. So the rule is that the condition is chromosome, the comparison is on chromosome either side, and the value is HS7. So if either end of the link is HS7, this rule passes. And we're going to apply the following condition. We're going to change the link color. Static change is always applied. That's just one of the options that the wrapper gives you. And we're going to make it black, okay? We're also going to add a second action. So rules can have multiple actions. Anything within these actions are just applied, okay? Because this rule passes. The second action will be to change thickness to 8. So now let's back up a bit. First action, select was make it black. Second action, make it thicker, make it thickness 8. And we'll have finally a third action. And that is the Z depth. The Z depth, if you can think about it, is basically the index of drawing things. You know, how far it is from the screen towards you. The larger the number, the closer it is towards you. In other words, it's drawn after whatever is underneath. And so the Z value for these points will be 10. By default, the Z value for everything is 0. So anything with a number bigger than 0 is drawn later. I picked 10 because later I might decide, I need something in between, so I would pick 5. If I picked 1 for this, I would achieve my purpose and have this drawn on top of everything else. But because this has to be an integer, yes, blame me, the developer, they have to be integers. I couldn't have a value of 0.5. So Z is 10. That's the next one. Okay, so here is that rule for the links. So notice if I zoom in, oh, I'm not zooming in. The black links are drawn on top of the gray links because they have a Z value of 10. And the Z links are gray and transparent. In fact, you can't quite see very much detail in those links. We could have applied some transparency to the black links if we wanted to. That will help you texture this area here where they overlap. So we come to this option of putting tracks on top of other tracks, using other data. So remember for the copy number tracks, what we're showing is we're showing the average copy number in windows of 5 megs. Now, a lot can happen in 5 megs, right? The average, there could be small regions of very positive copy number. There could be small regions of very negative copy number. And we're just averaging it out and we get 0 and we think nothing is happening, but in fact, a lot of things are happening. So it certainly would be useful if we had a handle on maybe the minimum and maximum values of copy number across smaller windows so we could figure out whether there's variability there. In item 34, titled overlay, we're going to look at that. So we're going to add a data plot, another data plot. We're now up to 5 2D data plots. And we're going to place the radius exactly where the scatter plot is for the copy number values, so 82 to 94%. It's going to be a histogram. For the input data source, it's going to be the file that gives me the minimum copy number across 1 meg bins. We're going to make it red. We're going to make a transparency of 0.2, so that means 20% opaque. It's going to be mostly transparent. Now, this is the minimum. So what I'm also going to do is I'm also going to create a rule for it. But just before I jump to that, I need to specify the minimum and maximum values in the same way that I did for that histogram to make sure that the axes of the overlay are exactly the same and match up with the axes of the scatter plot. Otherwise, the max axes would be mismatched and the overlay wouldn't do its job. So once I've specified the minimum and maximum options, Right now I'm drawing the minimum, so I'm going to decide that I only want to draw the minimum for points that are lower than minus 0.15, which means the rule will be any points above this value will be hidden. So the goal of this particular overlay is to show the minimum values in case they are less than minus 0.15. I will do the same thing for the maximum values. I will pick the same radial position as the copy number variation scatter plot. It's going to use the maximum values data set. These are going to be blue. Same transparency, 20%. Minimum and maximum values have to stay the same and match up with the minimum maximum values of all the other overlay and the other scatter plot. And the rule now will be anything below 0.15, so the negative values are going to be hidden. Okay, so I've got two plots that I've added. I've added the red histogram in exactly the area of the scatter plot track. I've added the blue histogram. And in each of those, the positive values for the red histogram and the negative values for the blue histogram are hidden. So I'm only seeing positive and negative values where they are quite different from zero. If I zoom in, I can see, for example, what's happening here. There are very small positive values in this window that are bigger than 0.15. And there is obviously tons of minimum values that are even smaller than these, because this is just an average. I can get a sense of the fluctuation of the negative and the positive, and note that there's quite a lot. The maximum positive value looks like more like a half, whereas the minimum negative value is closer to 1. So this is a good way of demonstrating the variability in your data. If you wish to do so visually, you're of course free to compute that variability and then draw it as a range or draw it as a quantity with, say, a histogram or scatter plot, but now where you're drawing the variability quantity as opposed to the data to show the quantity explicitly. Okay, for those who really want their cytogenetic bands and do not feel in their genome home without it, let's add them in the next cytoband image. Very straightforward. In the ideogram menu item in the front panel, you would scroll down to cytogenetic bands. You would select the cytogenetic band file that I provided. You would say no to convert bands from bed. You would specify no to band transparency, meaning that the bands will overwrite whatever the color is of that ideogram. And then there you go, you have your bands. Okay, just these are the low resolution or the high resolution bands. There's hundreds of them, so I can't remember whether that's the low or the high resolution band set. The red bits are the centromeres, and the where there are blue, those are for the acrocentric chromosomes with just one arm. That's the conventional colors used by the UCSC genome browser when you look at the chromosome ideogram when you are scrolling across the human genome. It's the same colors. Let's filter out some chromosomes, because like I said, you don't always want to draw everything. Generally, it's a good idea in your karyotype file to define all the chromosomes you have on hand. And then if you only wish to draw data on one or two of them, use this filtering facility as opposed to only generating karyotype files for those two chromosomes and only having data files for those two chromosomes. Zoom 1 will be the file example. And this is very straightforward. In the ideogram menu item at the front, you would just put a semicolon delimited list of chromosome names to specify which chromosomes you wish to draw. And by default, it'll draw the entire chromosome. Below, you see that, for example, there's a for example that shows you that you can specify the actual crop range that you want. So if you only want to show a portion of chromosome 1, you would have a colon and you would have 1 to 1,000. That would be the first kilobase of chromosome 1 shown. In terms of the scale of the human genome, it would be more like maybe 10 to 20 megs. That would probably be more sensible. But know that you can provide intervals in this field. You can also provide comma-separated list of intervals. So you can take a chromosome and chop it up into pieces, and then those pieces get glued together by Circos and shown as small chunks of that chromosome. So this is why there's a semicolon here, because a comma is used for something else in this field. So once I do that, I decided 4, 5, 6, 7, 8, 13, 17, and X. You see that only those chromosomes are drawn. The data has now more room to breathe. The bins are larger. So, because 1 meg on this axis is now, I don't know, 3 times as big as the 1 meg was in the previous image. So finally, what we're going to do is apply some rules to change the links. We're going to make all the links thicker and remove the intrachromosomal links. And this is item 37, zoom 2. So in the link track, we're going to make them all gray. So this is a very common way of applying rule. You need to change the way that the default data point is drawn. Okay, so by default, it'll be gray, and it'll have a thickness of 8. Okay, so instead of black and thickness 4, it'll be gray, thickness 8. And then I will add a rule. Intrachromosomal links will have their visibility change to no. And notice what's happening is with the rule before, I want to not only make them black, because remember rule 1 changed the links on chromosome 7 to black, but I also want to keep testing to make sure that there's no intrachromosomal links that include chromosome 7. So this is why the continue flow is set to yes, because I want to test, because it's quite possible for a link to be black and still intrachromosomal. That's why the continue flow is yes. So testing for intrachromosomal, change visibility, no. Okay, hides it. And here is the solution to that. No intrachromosomal links, so all the links are between 2 different chromosomes. By default, they're gray and thick. And then the ones on chromosome 7 are black, using the rule we've already written before. And with the additional rule we just wrote now, all the intrachromosomal ones have been removed. Okay. So this part was about using Galaxy in the wrapper, which will continue to be developed and implement more features of Circos in the wrapper. Your option doesn't end with Galaxy though. Galaxy makes it possible to download the configuration of any image and then run Circos locally once you've installed it and continue modifying it. So it's very helpful in setting up a template for you and then tweaking and then letting you tweak it to your personal needs. So typically what winds up happening is we've been doing this. We had some data files within Galaxy Australia. We filled out a web form, and what that web form does is it generates a configuration file that you don't see. It runs Circos, an instance of Circos, which generates the image, and then Galaxy Australia gives you that image. But you can export the config, you can edit the config, and then you can run the edited config and feed it to a local installation of Circos and get your image. So let's take a look at how this happens. In the output tab, you would select yes to configuration archive. That basically lets you download all the definition of how that image was created. And this is ready for you, item 37 Circos comp files. And if you click on the floppy, that's that floppy, you get a turbo. And if you unpack the tarball, you have two directories in there, conf and data. In the conf directory, you get the configuration files, and these define the image. They have all the information required to create, to determine how the image is formatted. And then in the data directory, you have all the data. Galaxy renames the data to data-01234, but these correspond to the data files that you have uploaded. Let's take a look at what it would look like when you were running Circos locally. It's very straightforward once you have Circos installed. Essentially, you'd be in the directory where you've unpacked the tarball, so you would see the conf and data directories. You would then run Circos. You would point it to the Circos conf file that Galaxy created, which was in the conf directory, like this, with the conf flag. Circos would run, blah, 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 and it would say, thanks very much, come again. It would create a PNG file, and then you would see the PNG file, and that would be exactly the PNG file, the bitmap that Galaxy created, okay? So you could just duplicate Galaxy, call to Circos, and then tweak it. How would you tweak it? Well, here is what the Circos conf file looks like. Basically, this configuration file, this is the root of the configuration file, and it has a lot of the features that you would have already seen in the web form, plus a couple of other ones. There's some includes that include color definitions and parameters that I don't really want to go into. But for example, here is a chromosomes variable that's defined. This is the list of chromosomes we're going to draw. This is from the last image. And there are some other includes. One of them is links.conf. And links.conf is this file. This file, by probably no surprise, defines whether to draw links and how to draw them. All of these files are structured in blocks like this. So a links block inside a links block is a link block. Okay, you could blame me for these silly conventions. Plural, singular. Here is a link track. The file is this. This Galaxy handily comments this out and tells you what the original one was. The radius is 0.7 r relative, 70% out towards the end of the circle. Here is the color, here is the thickness, and so on. And here is the rule that, or two rules that we applied to those links to make the ones that are on chromosome 7 black, thick, and on top. And this is the syntax of the rules as implemented underneath, and Galaxy Wrapper writes these rules for you. You don't have to remember how to write these rules, but just know that you can write much more complicated rules than this if you want to run Circos locally. And here's the second rule, whether the link is intrachromosomal. If it is, then I don't want to show it. This is the action, show no, don't show the data. This is the action for this rule, color, thickness, and Z value. There's also a data.conf file, and the data.conf file contains all the two-dimensional tracks, the histogram, the scatter plot, and so on. And these are in plots blocks. Here's the first one. It's the seg-dup count. This is a histogram, if you remember, 72% to 80% of the circle. Here's the light gray color. It's filled under. Here's a rule. If it's bigger than 20, fill it with RGB value 000, so black. And the rule blocks, here's some background blocks. One background from 0 to 100% of the thickness of the track, make it this, which is a very light gray. Okay, so that's a plot block. And then there would be other plot blocks below this that use different files and have different specifications for those tracks and different rules and so on. If you want to change, for example, the order of how the plot blocks are drawn, you could just go into this file and move this plot block to the back of the list, and it would be drawn last. That's one option. Or, which the wrapper doesn't implement yet, but soon will, you could add a Z value to this plot block to be, say, 15. All the other plot blocks have a Z value of 0. So this one will be drawn last because it's the index of the order of drawing. Okay. So here's a very kind of handy way to make edits on this file without having to remember the structure of the file and all the parameters that are used. You can look at the online documentation to get a sense of what these parameters are. And generally, there's a lot of tutorials and a lot of examples online. And you can use one of those as the template to start your own project. Okay, this brings us to the end of part 2. So I'm happy to spend the next little while taking more questions or going back to anything that you would like to see again. Okay, let's look at some questions. Yes, you can add a scale and an axis on the scatter plots. Yes, there's it works very similar to ticks. Essentially, you can create axes or grids at specific positions. You can have groups of these axes grids, specific positions, absolute spacing values, let's say every 0.1, or relative spacing values, let's say every 10%. And you can color each one separately, so it's quite flexible that way, and it goes in axes blocks, and there's a ton of it on the online tutorial. The Galaxy wrapper currently only supports relative axis spacing, and we're going to add absolute axis spacing and positional axis spacing as well. Okay, this is a long one. Could you use rules to filter an expression data track on both expression level and significance so that you could hide all data points above a certain p-value and below a certain expression range? Or can the rules filter only take one data column at a time? Okay, this is a good question. Very good question, and the answer is yes, you can, but the way you would need to define the data file is slightly different. I'm going to back up to where I defined my data points here. Hold on a second. I'm going to go here. Okay, so if you remember, the copy number data file was this, chromosome start, end, and value. What I can also do is, in addition to the value, include an optional parameter, let's say P. And this value these values might look something like this. Whatever, okay? So each data point would have this parameter, P. Now, this parameter is just, Circos reads it in and it knows that every point, there's a parameter called P and it's defined to be something. And in your rule, you can then have a rule that has two conditions. If P is less than 0.05, let's say, and value is less than minus 0.2, then show it. Otherwise, don't show it. So that is how you would combine two or more different aspects of a data file together in one rule. This is something that's not supported by the wrapper yet, unfortunately, but I'm going to talk to Helen and we're going to work on ways to bring some of this functionality in as easily and as quickly as possible. And so in general, I'm just going to continue answering this question because it's a good question. And even though the answer is maybe slightly technical, I think it's of value. Data points can have other parameters, okay? A, B, C, 1, 2, 3. And you can define these parameters to be whatever you like that are relevant to you. And then you can test these parameters when in the rules. Now, the neat thing about rules is that they're actually almost too powerful for mortals, right? Because they also allow you to change the value of the point. Not only just test whether it should be showed or not, or colored red or blue, but you can change the value. So I could say something like, have a rule which changes the value of this point to p, to the p-value. So now I can have a track which plots the p-value and not the value in the fourth column. That's really powerful, actually, which means that you can centralize all your data in one file, and all the values are stored, or all the different columns, if you will, are stored as these parameters, okay? So that's good question, and I hope that that answered that question. I'm just scrolling through questions. Oh, yeah, there's more on the next page. Okay. Can you tell how Circos is drawing the ribbons connecting different chromosomes showing sequence identity? Does this information need to be specified explicitly, or does Circos determine this using the genome sequence? So the second question, the Circos determines nothing. It only draws what you show it. Now, sequence identity. So if you're paying attention to the answer to this question, you may already be thinking ahead and saying, wait, maybe I can have a parameter at the end of links, which is the identity of level of this alignment, right? Something like that. Yes, you can. That's cool. So now you can have a rule which says, all right, draw me all these links. Anything with an identity less than 0.95, don't show it. Great. Anything with an identity, anything that remains, color the link based on the identity. So remap the identity values to the fill of the ribbon. So it might be from light red to dark red. It might be from purple to green, some kind of a brewer palette color, okay? If you're feeling really cheeky and you want to anger me, you would choose a rainbow color, and then I would tweet about it, okay? So this is how you would do it. You would include a parameter that had the identity or any other score. For example, there might be some gap number, let's say 5 gaps, gap number 2 gaps, gap number 0 gaps, and you might say, all right, I want identity more than 95% and gap number to be no more than 2. How do we ensure that the colored scatterplot points are drawn above the gray ones? Yes, you would set the Z value of the colored points to be larger than the gray ones. And let's just scroll down to the I'll give you an example. Basically, you would have, in the rule for the scatter plot, which I'm not showing here, you would just have something like Z equals 10. And so if this was the rule that colored the plot, the point blue, right? Then it would assign the point a Z value of 10. All the other points by default are 0. So these would be drawn on top. That's how you do it. And unfortunately, the wrapper doesn't support Z values for 2D data tracks. It only supports them for links right now. So I think I can work with Helen pretty easily and add them for both kinds of tracks. How do we generate the Circos friendly data? From comparing a couple of bacterial draft assemblies, do we first need to run a core genome comparison, then import its output to Circos? Yeah, whenever your question implies any kind of analysis, the answer is, sorry, you have to do it not in Circos. And then you would take that alignment and draw some kind of a Jupyter plot, a plot that looks very similar to this plot. Okay, this plot, except that on one side you would have one bacterial chromosome, on the other side you would have another bacterial chromosome, and then all the links would correspond to the alignments. Now, your alignments might be really messy. It might be really full of gaps. You might not care about all the messiness of the alignments. So in the utility section, let me just jump to that. very quickly, the utility section. The utility section, I'm looking for it. I'm sure some of you have already found it. This one here. In the utility section, there is an option to bundle links. Bundle links, reduce numbers of links in data sets before plotting. What this will do is, this is just a script. There's no magic behind these menu items. These are not the answers to life and universe and everything. It's just a script I wrote, okay? So just be aware of that. What it does is it groups links together into one big link with certain rules, like, okay, well, if these links correspond to, let's say, alignments, and these alignments are closer than a certain distance, like half a kb, then group them into one. Okay, otherwise don't. There's also some filtering there that says, well, if the links are smaller than some value, don't show them. But that's something you can achieve in Circos with rules. So if you take your genome alignments, combine them with this bundling links, you get what I'm talking about. Now, I can go back and give you an explicit example of this, which is right here. Here. Let's show this one. Okay, this is cool. So remember, this was the one of the art exhibits that used Circos, and this is a great example of bundling links. So these panels, these are 35 centimeter by 35 centimeter panels. There's 6 of them. So these circles are not that big, right? They're maybe 5 centimeters, 6 centimeters across. And what this is this is the genome alignment of the chimp. See, that's a monkey, obviously a chimp, to human. So the top half of the circle is the entire human genome. The bottom half of the circle is, oh, I'm sorry, I think it's the other way around, right? The bottom half of, wait, hold on, let me write, oh yeah, sorry, the top half of the circle is the human genome. The bottom half of the circle is a chimp chromosome. And you see the alignments between the chimp chromosome, and the human genome. And because chimp and humans are very similar, basically the entire chromosome of the chimp goes to chromosome of the human. However, when you go to something like a chicken, most of us are very different from chickens. The alignments are going to be quite scattered and quite small. Now, in reality, there are millions of alignments here that are very, very tiny, that you would not be able to see when drawn at a scale of 5 centimeters. So the bundle link feature glues those together and basically gives you an overview of the links kind of at a zoomed out level. And then if you zoom in, you realize that, oh, that's just one link, but many links stuck together. Okay, so that's how you would do it. This is also a closer up view of this is here, where you see the dog chromosome at the bottom and the human genome at the top, and you see that, oh, cool, dog chromosome 1 at the beginning is made up of whatever this is chromosome. This is, the human genome starts here, 1, 2, 3, 4, 5, this might be 20, so there's a bunch of 20, maybe there's 11, here is chromosome 19, and so on. So you can quickly see the syntenic blocks. Chromosome 7, for example, of dog is mostly a chunk of chromosome 1 and whatever this is, 19 or something, okay? Okay, I'm looking at your questions. Okay, are there any other questions before we wrap up? I will post answers to all the questions, so if you think of one after we're done, don't worry about it. I'll still answer it. Okay, Luke is writing, for that last example, how are the colors generated? Right, for the links. Okay, so for this example, for the dog versus human example, if that's what you mean, you see that all the human chromosomes are colored with those UCSC conventional color palette, which you are free to love or hate. And think of the data files. The data files define the link as between a human chromosome and a dog chromosome, right? So this might be something like, let's look at for HS1, because human chromosome 1, to CF6. And then the rule would be something like, all right, color the link based on its human chromosome. So if it's HS1, color it using the color of the chromosome. And I have conveniently created color names that are named HS1. So you can just assign the chromosome of the beginning of the link as the color, and it will come out brown. So that's one of the, that's something that the wrapper doesn't, I think, support easily, but it could, and it will make sure that it does soon. So that's how they're generated. The colors are picked based on what human chromosome they fall on. Choice, okay, somebody else, choice of colors for people with color blindness. Is that what you're gonna, color blindness? Yes. Yeah, yeah. I just spent an hour talking to people about data visualization and color blindness came up. Thanks, Musulev. Unfortunately, the UCSC color palette is not colorblind safe, basically meaning if you can't distinguish red and green, for most part, that is the color blindness that affects people. You are stuck. And I have a simulation for color blindness. I hope this comes through. I'm not sure if this is being shared appropriately with the meeting software, but I just changed my desktop to simulate what people with deuteranopia have. So these people are missing the middle wavelength color receptors, I believe, so they can't distinguish red and green very well. So what you're seeing is you're seeing everything in either blue or yellow, and there's a bunch of chromosomes that can't be distinguished because you just don't have the color bandwidth. So what do you do? Well, you have to pick a color palette that doesn't count on red-green differentiation. And I actually don't have one of 24 colors. I have one for 12 colors or so, which you can find on my webpage if you search for my name and color blindness, but not for 24. So one way of doing that, it starts to get very hard once you get more than 10 colors to try to come up with a number of colors that people complete color blindness can differentiate. One strategy is to use a light and dark version of a color. So if you can pick 10 colors that people can differentiate, and you can then take a very light version and a very dark version of that color. And so they will perceive that as a luminance difference. It's going to be hard and it's going to get a little sketchy, but you know what? It's already pretty sketchy with 22 colors or 24 colors if you don't have color blindness. So I think that you could probably find a combination that works well. Okay. So just on the topic of color, there is a lot of support for Brewer palettes within Circos. Brewer palettes are color palettes that have been created by an individual, Cynthia Brewer, who worked in cryptography, and they are commonly used for encoding categorical data and qualitative data and continuous data. They're used in R a lot. If you've seen color palettes like set 1, 2, or 3, or paired 1 and 2, those are Brewer palettes. Circos supports them by name. You can encode values with Brewer palettes really, really easily. So whenever you are thinking about using color to encode information, please do not try to make your own color palette. There's lots out there that are available that have certain properties that help make the relationship between the color and changes in data less ambiguous. how can you export as SVG rather than PNG image format? No worries there. You look down to the output tab and you click yes to SVG and no to PNG. And the SVG file it respects your time and patience, and it places every track in a different layer. So if you bring it into Illustrator, you have everything in different layers or groups. And so you can turn their visibility on and off very easily, and you can manipulate things a lot easier. So that's pretty easy. You can, if you like, then add some JavaScript to the SVG, and that's up to you to do, to implement some basic interactivity, like if you click on a data point, it blinks or something. Any other questions before we wrap up? There's probably somebody out there who's like, I wonder if I should ask this, but I'm worried that my life is going to not go well after I ask it. No, it's going to go fine. Go ahead, ask it. I'll wait 10 more seconds for that individual to start typing, and then we'll stop. Yeah, there you are. Okay, tips for getting into the field of data visualization. Oh dear, that's okay. Well, so first of all, why do you want to get into the field of data visualization? Is it something you truly love and are passionate about? Let's say that you are. Because it might seem like a really exciting, cool, funky thing. And if you're not passionate about it, then do something that you're passionate about. 2, pay attention to, there's lots of books out there. I'm going to try to give you an answer that you can't just Google in 2 seconds. Pay attention to things that you think are good visual explanations of things. Be aware of what you are seeing when you're looking at figures. Any graphic, look at its structure, look at its internal organization, and be sensitive to things that bother you. Develop that intuition in which you're bothered by something and you sense the bother before you even can think about what's really wrong with it. And after a while, this will come. And you will look at things and go, this is not the way to do it. I don't know how to do it, but I know it's not this way. And so what happens is that you're not really going to be following a set of recipes in data viz. Oh, if I have this kind of data set, I have to use a scatter plot, I use a color encoding, I use a Brewer palette, you see I'm a great data visualizer. No. You're basically then just cutting and pasting somebody else's work. If you were a writer, you wouldn't cut and paste another book, regardless of how many books you sampled into a new book. You need to be guided by the ideas of concision, clarity, avoiding things like redundancy, use concepts like Gestalt to try to figure out whether things are organized well on the page, and read about those things. Don't read about how to make a scatter plot and ggplot, okay? That's pointless, because at that point, you just know you need to make a scatter plot, and the rest is just, it's trivial automation, truly. It's the stuff that machines can do. And you have to distinguish data visualization that can be done by a machine and data visualization that requires a human in the loop. You do not want to spend any of your time figuring out how to do what machines do, because the machines are going to do it. They're going to take your job tomorrow. What you want to figure out is how to be more of that human in the loop, how to edit what the machine has made, and how to inspire and kind of help other humans do a better job at being human. So what that means is understanding how the data visualization is communicating, what it's communicating, trying to get a sense of the concepts, and trying to get a sense of the message of the explanation of the concepts. So in a way, if you're getting into data visualization, you're getting into communication by eye as opposed to by ear. You know, you're becoming an editor of drawings rather than an editor of words. And drawings can be interpreted as words in the same way. They're words or paragraphs or sentences and so on. There's a certain grammar. And without wanting to get too much into the details of it, because actually the details are not that useful because they apply kind of everywhere but nowhere at the same time. That is the kind of skill that you want to practice. So you can go out there and read some books from the greats and like Tufte or whoever, and internalize that as good rules, whether you like it or not. Then figure out whether you want to break any of those rules, and find your own voice of communicating with other people. And hope that that voice works. And be aware of how people are responding to your visualizations. And learn how to kill your darlings. In other words, if your favorite color is purple, be prepared never to use purple, because it's not about what your favorite color is, it's about what works. So those would be the tips that I would give you that aren't in some obvious 5 ways to start your career in data visualization listicles. All right, that was the final question that I was waiting for. Thank you very much, everyone, for your attention. I hope you've learned something. And I invite you to look at the website, the Circos website, go through the tutorial again on your spare time, working through the images, changing some of the values, looking at how the image changes, determining whether the image changes in a way that you like or not, and start your Circos career there, or end it if you felt this is not useful to you at all. That's fine. Don't waste more time on it. So with that, I will end my bit, and I hope everybody has a great rest of the day. Take care.
Well, thank you so very much to our presenter, Martin, and also to the Galaxy Australia team who's been assisting behind the scenes. Thanks to our local facilitators around Australia, and of course to our participants. We hope you found today's workshop fun and enlightening. And a reminder, please, to fill in the evaluation for today's session by following the link at the bottom of the discussion board and on your schedule as well. It's there. It's really important to us to know how you got on. The recording of today's session will be available on the Australian Biocommons YouTube channel, and you'll be notified when that goes live. Now, for future Australian Biocommons training, please head to our website. I'll put up some info there. You can follow us on Twitter, subscribe to our e-news, and the website will tell you all of the venues at which each training event is heading to. And if your institution is not there, then why don't you volunteer to assist us as a facilitator in the future? So we're very grateful for Martin today to join us. We're very grateful to all of the institutions who have provided us with the wonderful facilitators. And this workshop was really made possible by Martin's Australian visit that is supported by the Australasian Proteomics Society. We'd especially like to acknowledge Canada's Michael Smith Genome Sciences Centre at BC Cancer for Martin's time and expertise. Thanks to the Galaxy Australia team, including staff from QCIF and Melbourne Bioinformatics. And with that, I'll wrap up by thanking our funders. So the Australian Biocommons is enabled by NCRIS via Bioplatforms Australia funding. So thanks once again, everyone, and goodbye.